Thank you very much. I'd like to thank the organizers for inviting me. It's a pleasure to be here. Also, I'd like to say, of course, that I'm going to be talking about joint work with Toby. And now, as Toby explained last time, what we're interested in is understanding what happens to embedded minimal disks. Now, of course, when the curvature is bounded for this disk, then the disk locally just looks like a graph. So the picture's clear and very simple. So in order to understand this, what you really need to understand is what happens when the curvature is not bounded, what happens when the curvature gets large. Okay, so that's the point of this talk, is beginning to understand what happens when the curvature gets large for an embedded minimal disk. So in order to save myself some trouble throughout, sigma is always going to be an embedded minimal disk. It's almost always going to sit inside a ball of radius r, centered at the origin in R3, and its boundary is going to be in the boundary of the ball. There are a couple of times where it's convenient to make it in the ball of radius 2r or something like that, but I'll assume that nobody would be so upset when that happens. Now, just to finally set notation, it's also going to be useful. These are extrinsic balls. They're ordinary Euclidean balls. It will be useful to deal with intrinsic balls. So if I write a script V, this is going to be an intrinsic ball inside sigma. Okay, again, often we'll often assume that the origin sits in the surface, so centered at the origin. Now, what we'd like to understand first of all, or what I'd like to describe a little bit about in this talk, first of all, is what happens when the curvature gets large at a point. Okay, so what happens nearby that point? So it gets large. Let's say that the curvature gets large. Let's say at the origin, so at a point, and we'll normalize it to the origin is large. Now, when this happens, a multi-value graph develops. So Toby explained a little bit about these multi-value graphs. So let's say n value. This is another. I'm going to write values like this. So an n-value graph forms nearby. And when I say nearby, I mean on the scale of the curvature. So the scale of the curvature, that's approximately 1 over. Okay, so as the curvature goes to infinity, the scale goes to 0. So it's a very small piece at that point of a multi-value graph. Okay, so this is the first thing I'm going to want to talk about. Second, once I have these small pieces of multi-value graphs, yeah, I'm not sure how long I could have kept that. Just needed to take this out before I go through airport security. So now, okay, so the first thing says that if the curvature gets large at a point, then a multi-value graph, an n-value graph, forms nearby this point, and this all happens on this scale, the small scale. Okay, I'm going to make this precise in a minute, but just as a rough statement, let's deal with this. This only happens now on a small scale. So how am I going to connect this to the rest of the picture? Okay, so the next point is extending this. So this meaning this multi-value graph almost to the boundary. Well, the boundary sits in a ball of radius r, so almost to the boundary of the ball of radius r, where almost just means now, I'll just say a ball of radius r divided by a fixed constant. Okay, so these two together show that anytime, these two pieces together are going to show that anytime the curvature gets large at a point, a multi-value graph forms on a small scale, extends all the way out to the large scale. So near where the curvature gets large, we get these multi-value graphs, and they exist on a large scale. Okay, so we take this, motivated by this, say, we're going to say that these multi-value graphs are the basic building blocks for an embedded minimal disk. So an embedded minimal disk is built out of these pieces. And then a large part of the question is going to be, well, okay, I've got all these pieces, how do they fit together? Okay, that's what Toby's going to address tomorrow. How do these pieces fit together to give compactness theorems, convergence theorems, removable singularity theorems, all of this. Okay? So for today, this is what I want to focus on. Now, I'm going to break this up into 3 parts, A, B, and C, and then I will sort of address these in the order A, C, and B. And the third part is I'm going to show you a tool which we use in proving B, which we call estimates between the sheets. I won't really say why we call it this or anything until we get to it, but I think it'll be clear. This is a tool which we are going to use in B. And so in order to simplify the approach to B, or make a reduction in the argument for B. So now, A is this first part, finding these graphs on this fixed small scale, is the most accessible part of these 3. It's probably also the part which I can give the most self-contained explanation of. So I'd like to concentrate on that. That being said, this second part, extending the multi-value graph, is by far the more serious part. And there are a lot of issues in here which I will not have an opportunity to address. But perhaps it might even motivate you to look at the papers or ask me afterwards. Okay, so that being said, let's start with A. Okay, so this is where the focus will lie. This is probably where, given enough time, the focus should lie. Okay, so now, how do we find these multi-value graphs? I'm going to give you 4 sort of fairly elementary steps, and then or results. We'll build these 4 to combine these 4 to obtain the argument here. Okay, so let me remind you of a couple of things. Okay, so first of all, we're going to need to relate the areas and curvatures. Okay, so for the time being now, I'm going to work in large part with these intrinsic balls. Okay, so a rough outline of this is that these multi-value graphs are actually going to be found inside one of these intrinsic balls. Okay, so let me, of course I shouldn't precisely state the theorem. So the precise statement is CM2, I guess there's some loose ordering of the papers, so this refers to the second paper in the sequence. Okay, so the theorem is, this is the existence of a multi-value graph on a small scale, and the theorem says that given, well, we're going to say given a couple of constants, well, if you have this multi-value graph, there's sort of 3 useful constants to talk about. One, of course, is this n, the number of times it winds around. A graph, well, the minimal graph equation is particularly well behaved if you have a nice bound for the gradient. So I'm going to throw an epsilon in there. That's going to be the bound for the gradient. And when I say that, there's, of course, the number of times it winds around, and then there's how far out it's defined. So let me throw in a constant omega for that. So given these constants, then there exists another constant c, so that if, and now I'm going to say the curvature gets large, so if the sup of a ball of radius r0 intersects c, this is an extrinsic ball, of course, of mod a squared is less than or equal to 4 times a squared at the origin. So, of course, you'll recognize this as the sort of thing that you achieve using a blow-up argument. Essentially, this is saying that the maximum of the curvature is at the origin. Okay, so if you have this, and then I want to say this is large, so we'll say that this is equal to 4 times the large c squared divided by r0 squared. Okay, so if we have this says the curvature gets large at the origin, and here we've just sort of normalized so that that's approximately the maximum curvature. Then there exists an n-valued graph, sigma sub g, contained in sigma, over, and now it's going to be over an annulus. This is going to be an annulus of radius omega times r bar. R bar is going to be some constant. Take away disk of radius r bar. And now here, r bar is just something less than r0 divided by omega. With gradient less than or equal to epsilon. And in fact, we get slightly more. There's another condition which is useful later. And Okay, so this R bar is less than R0 omega. This is where we say it's on the scale. Right? Because notice R0 here is roughly, C is a constant. So R0 is just roughly 1 over the maximum of the curvature. Okay, so it's starting on that scale. Next I said nearby. Okay, so nearby says that the distance in sigma from the origin to this graph is actually less than or equal to 4 R bar. Okay, so this is the nearby. Okay, so this is the precise statement of the theorem. So just to recap, here we're saying the curvature gets large. R0 is supposed to be a large constant. Okay, R0 is a small constant, so 1 over R0 is large, so the curvature is large. If this occurs, then one of these n-value graphs develops very quickly nearby the origin. And the ratio of the annuli, which is over, is this omega, which we could have taken to be large. And in fact, the graph has gradient bounded by epsilon. Okay, and now one other remark. Here and many other times, there's no reason, of course, that this would happen to be a graph over the x3 equals 0 plane. You know, it could have rotated any which way. So of course here I also mean that after a rotation, I can choose it to be over this plane. So a multi-value graph over some plane, why not? Okay, so this is A, the precise statement of A. Given that you can take any n you want. The price you pay is if you want more rotations, this curvature is going to have to be bigger. So the surface lifts up and then just stops, and then so it's nice and embedded, but it's not like like an Enifer surface or something where it comes back through itself. It's not like that.
So this is at most n sheets?
No, at least n sheets.
At least n sheets.
Okay, so right. So what does this look like? This is going to look something like this, right? And it winds around n times, at least n times. It may continue to wind around, but we couldn't have predicted that it would from this. And the ratio, and now it looks like a graph out like this. This is some R bar, and it goes like that all the way out to omega times R bar. So of course here I'm thinking omega and n are large numbers. Epsilon is just to say something greater than 0. Okay, so here we found this multi-value graph.
What I'm worried about is, for example, I mean, if it were a plane and A was identically equal to 0, it looks like your hypothesis is verified.
No, because A...
Oh, A of 0 has to be equal to that.
Has to be equal to this. Right. Right. Yeah, so if the curvature gets large, this is the only time you can find one of these. Okay, so this is the precise statement. It says that if the curvature gets large, remember R0 is small, so A here is large, then on this scale, a multi-value graph develops. It goes around at least n times, and it lives at least from some R bar out to omega times R bar. As A at the origin if this were to go to infinity, take a sequence where this goes to infinity, this R0 would go to 0. Okay, so these graphs would disappear, and we'd be left with nothing. Right? That's why the extension result is important, of course, right? We need to maybe start on this unbelievably small scale. How am I going to get something that I actually see in the final picture? Okay, that's why we need to extend. Okay, so now, if this is true for some R0 less than this capital R out here. So this is as long as R0 is less than capital R. Okay, so, right. Right. Okay, so notice that like in the picture of the helicoid, for instance, where the curvature is just 1 at the origin. If you look on a small ball, it just looks like it doesn't look very complicated. But as you look on larger and larger balls, you get the multi-value graph developing more and more. And that's because you just needed to take R large enough in order to start seeing the picture develop. Okay, so Okay, so now I'd like to describe how you approach this, why this should be the case. Okay, as a rough outline, this is what's going to happen. First, I'm going to use, notice this is saying that I have an upper bound on the curvature. I'm going to use this upper bound on the curvature to get some control on intrinsic balls. I'll show that the intrinsic balls, the area and total curvature of these grows polynomially. In fact, at most like r to the fifth. Using this, I'm going to show that if I look in most directions, the curvature is decaying quadratically. This is going to give me large pieces which have quadratic curvature decay. Then I'm going to use the fact that the curvature is bounded from below to say that there have to be a lot of these pieces. It's going to follow that two of these pieces are close together. Since they're close together but disjoint because these things are embedded, they're going to have to basically be stable. Since they're stable, they're going to have better curvature estimates, and then we'll show they have to actually be very flat. Once they have to be very flat, I can build out the multi-value graph. If you think, how are you going to fit something with very, very small curvature, a large intrinsic thing with very small curvature and a small extrinsic set? The only way it's going to happen is this spiraling thing. Okay, so that's going to be the punchline at the end. Okay, so as a rough outline, that's what we're going to do. So now let's start with this. So the first thing we need to do is get some control over these intrinsic balls. Okay, so I'm going to begin by just recalling some elementary relations between area and curvature. Okay, so now this is a disk. It's minimal, so it's got nice non-positive curvature. So I can just use the exponential map as a diffeomorphism, and I can write that the 4 times the area of a ball of radius r minus pi r squared is actually just equal to, this just comes from integrating up the Jacobi equation and using the Gauss equation. It's just twice the integral from 0 to r times the integral from 0 to s. Sorry, the integral from 0 to t of the integral over the ball of radius s mod a squared. Right, so if you differentiate area once, you get length. Differentiate area twice. Right, so when you differentiate area twice, then you get the integral of the geodesic curvature. But the integral of the geodesic curvature is just over the boundaries, the same thing as the integral of the curvature on the inside by Gauss-Bonnet. Just think of it that way. Okay, so this just comes from integrating that up. And then I want to take this and integrate by parts twice. Do two integrations by parts against the function r minus t squared. And this is just equal to the integral over the ball of radius r.
So why curvature squared?
I'm sorry, just 1 second. What was it?
Why curvature squared from the discussion you just gave?
Yes.
Gauss curvatures.
Yeah, that's right. These are the principal curvature squared. So the Gauss curve. Right.
Okay.
Yeah. Right. Sorry. Okay. Right. Okay. So I've got that the area. So just first, a basic principle: area and total curvature, they're basically equivalent, as long as we're willing to say to go to double balls or something like that. Second, by integrating by parts twice, I get this nice formula here. Okay, so now this is what's going to be useful for actually bounding the area, and then of course that means also bounding the total curvature. Okay, so now why does this imply an area bound? Let me give one example first, an easy example first where it implies an area bound. An example where it's easy to see. So first, why don't I suppose that the ball of radius r is actually stable? Okay, so now I'll try and experiment with different colored chalk, because I'd like to write some things sometimes, but have you be able to ignore them other times. So let's say, because it's stable, I'm going to write in yellow. Since it's stable, that means I can, I get that the, right, so remember the stability inequality says the integral of mod a squared times any function, cutoff function phi squared is going to be less than or equal to the energy of that function phi squared. This is the stability inequality. Okay, so because of this, I can use phi equal to r minus r. R is the outer radius, little r is geodesic distance. This function vanishes on the boundary. So let me plug this in here. In the stable case, this is less than or equal to the integral over the ball of radius r of, this happens all the time in my calculus class too, where the chalk just keeps breaking. I've managed, I think, to convince my student it's because of truly exceptional strength. So, right? Rather, I'd break that too. So now, but thank you. Okay, so now, this is from the stability inequality. This is just a constant. The gradient of the distance function is just 1. Right? So this is just equal to the area of the ball of radius r. And now we notice that we have 4 of them on one side and 1 on the other. So subtracting it off, we see that if you have a stable thing, then in fact the area of an intrinsic ball of radius r is less than or equal to 4 pi over 3 r squared. Right? So stable implies quadratic area growth. Okay, so right now, in the situation that we have here, of course, it's not the intrinsic ball is not stable. However, it does have bounded curvature and it is embedded. So what we're going to show is that we can decompose it into a couple of different parts. A large part of it, which is going to be stable, and then some part we control, where we control the amount of curvature and area, which is sort of, we'll just ignore that. Okay, and then repeating the same argument, but now with an extra term, we'll get that polynomial area growth. Okay, so that's going to be a point that we'll come along to in a minute. Notice, of course, that once you have this bound for the area, of course, that also implies that you get bounds for total curvature of at least on half the ball for a stable surface. And therefore, of course, you can, using a logarithmic cutoff trick, you can get small total curvature and you can show a curvature estimate or something like that. Okay, so now, that's the first thing I wanted to know. Now, in order to, so I just hinted at where I was going in order to apply this. I was going to show that if I have this intrinsic ball that I'm worried about, that a lot of it is stable. So let me say how that's going to go. Okay, so the next thing I want to use is that if I have 2 disjoint surfaces and they have bounded curvature, but they come close, that both of them are going to be stable. Okay, so this is something that's familiar for geodesics and maybe slightly less standard for minimal surfaces. But if you just think of the geodesic case, I think it's fairly clear. So let me state explicitly what I mean here. So let me suppose that I have 2 balls, a ball of radius 2 about a point P, and then another intrinsic ball of radius 2 about a point Q, which are contained in sigma. Let me suppose that mod A squared is less than or equal to 4. Right? I'd like to normalize this. So over here, it's convenient to normalize. I can rescale the whole picture to make the curvature at the origin equal to 1. So that means I rescale by C over R0. Okay, this is probably a bad idea, but here it goes. This is an equivalent statement. Okay, so now I've made the curvature at the origin 1, and the curvature everywhere less than or equal to 4. So this just dilated the whole picture. Okay, so now, if you have this, and these are disjoint, and the points P and Q are close, okay, so if I was writing this as a theorem or a lemma or something, I'd say there exists epsilon such that, then this implies, first of all, these 2 surfaces have bounded curvature. They come close, but they don't cross. That's going to force one of them to be able to be written as a graph over the other. Okay, so first, this means that the ball of radius 2 about Q contains a graph. A graph now means, say, normal exponential graph over the ball of radius, say, 1 about P, and now a graph of, let's say, of a function U. So that's the first observation. Second observation is that, in fact, well, here I have both of these things, they're minimal. They both satisfy a nice equation, but they're close together. Therefore, the difference, in other words, this function U, basically satisfies the linearized equation. But that's just the Jacobi equation. Right? The linearization of the minimal graph equation is just the Jacobi equation. So, in other words, L of U, here's this is the Jacobi operator. Right? So this is the Laplacian plus mod A squared plus the Ricci in the normal direction, which is 0 here because we're in R3. Okay, so L of U is approximately equal to 0. Approximately means to lowest order in U. Okay, now, notice that since it's embedded, u does not vanish. So I can assume that u is, say, positive. Okay, so now on this ball of radius 1 about p, I've got this positive solution, essentially of the Jacobi equation. This implies that the operator L is non-negative. In other words, this implies that the ball of radius 1 about p is stable. Okay, so, well, I lied a little bit because these weren't equals, these were tilde equals. So, in fact, what you can get is that it's almost stable. Right? You don't quite get the stability inequality over here, but maybe you get it, instead of with a 1 here, with a slightly higher number. So, like 2. Okay, but if I get it with 2, you'll notice from this argument, that would just give a bound of 2 pi r squared. As long as I got it anything less than 4, I'd be fine. Okay, so this implies that the ball of radius 1 about p is essentially stable. So I'll call it 1/2 stable because I've lost a factor of a half in my stability inequality. Okay, so this is the second ingredient. Now, I guess I have to go back over here. Okay, so the next thing I want to do is I want to use this to break apart my surface into a bunch of pieces. So I'm going to look at the pieces where I don't have anything nearby. Well, of course, if I have a piece and I have another piece nearby, then they're both stable. But if there's nothing nearby, then it's not stable, and what can I do? Well, it's all sitting in a ball in R3. So there aren't going to be that many pieces which aren't close to anything else, right? Okay, so let me say that. So now I'm going to get the area bound. I'm going to show that this is basically polynomial less than or equal to an r to the fifth. So the key for this is decomposition. Okay, so I'm going to break the surface into parts. So let me say that a point x in the surface, so here's a little point x in sigma. I'm going to say that x is bad. Let me suppose that this gamma sub x, let's say this is a vertical segment of length rho, where out here now I fix some rho greater than 0. It doesn't matter what. Well, it's going to be something that it comes out of this stuff over here. It's related to this epsilon. Okay, so I want to talk when it's close or when it's not close. Okay, so fix some rho greater than 0. And then I just define that given each point x, gamma x is a vertical segment pointing in the normal direction of length rho. If this gamma of x, get a little cramped. So if gamma of x misses sigma, then that's a bad point. Those are those isolated points. Okay, so if sigma intersect gamma of x is just equal to the endpoint x, then x is bad. These are these isolated points, nothing nearby. Otherwise, I say it's good. Okay, so now I decompose the surface. I can write sigma, say the ball of radius r intersects sigma, as a union of 2 parts. A bunch of bad balls. Right, I cover the bad set by a bunch of balls. And then what's left over is near itself. Okay, this is an oversimplified treatment, but suffice it to say that using this idea over here, A2, that if 2 things are near each other, they've got to be stable. That using this, you can see that what's left over is stable. Or say 1/2 stable part. Okay, so now, if it's in a bad ball, this says it's actually somewhat isolated in R3. Okay, so they're going to be approximately r divided by rho to the third of these. Okay, so this is some fixed amount. Okay, on the other hand, there might be a huge amount of this, but we have good control over it. Okay, so now let me plug this into. So let me plug this into this area bound A1, and now I'm going to get that the total curvature is going to be bounded by the total curvature of the stable part plus the total curvature on the bad part. On the stable part, I use this inequality. On the bad part, I just say, well, there's at most r cubed of these. Each one gives me some fixed contribution. So I pick up some constant times r cubed. That's it. Okay, so this gives me, we get that the area of a ball of radius r will be less than or equal to a constant. Well, I have the old r squared that I was stuck with from before. And now I get r squared times the amount from the bad part, so that gives me an r to the 5th. Okay, so there's the polynomial bound. This is saying the area of the intrinsic balls is going to grow polynomially here. Notice that if you just knew, as long as the curvature is bounded by 1, notice, of course, if you just knew that intrinsically the curvature was bounded by 1, you could have exponential volume growth, whereas this says it's polynomial. Okay, so that's the first, it's the third observation. Now, this, of course, said that total curvature also grows polynomially, right, because they're basically equivalent. All right, now, okay, so now the fourth part. So I said that this is going to imply that most directions are good. So let's see why that is. Yes? So over here, right, the total curvature, I get, it's an r squared times mod a squared. Okay, so I bound this by this quantity on the stable part, and that picks up a term like this. Okay, now the bad part, I pull out the r squared, and I'm left with the integral of mod a squared over the bad part. The total mass of the bad part is like r cubed. And so the r squared times the r cubed gives me the r to the 5th. The maximum of the curvature is 4 anywhere, so that just goes into the constant. Yeah. Okay, so, right, okay, so that's where that. Now, okay, so now let's go on to the fourth part. So I wanted to claim that most directions were actually good. In other words, most directions would see quadratic curvature decay. Okay, don't forget to ask that question. So most directions have quadratic curvature decay. What is that going to mean here? Okay, so right. So let me actually. I'm going to need first an estimate. So this is going to give something like most direct. You know, if you look in most places that the curvature is bounded, you get a nice bound on the curvature, the total curvature there. Okay, so but in order to go from a bound on the total curvature to a pointwise bound on the curvature, we need some kind of curvature estimate. So let me state that. Okay, so this is a curvature estimate. And so this just says, so if the integral over an intrinsic ball of radius r of mod a squared is bounded, let's say less than or equal to some constant c sub a, then the sup over the intrinsic ball of radius r over 2 of mod a squared is less than or equal to another constant c sub b divided by r squared, and of course c sub b depends on c sub a. Okay, so in particular, suppose that you had finite total curvature. This would be bounded as r went to infinity. This would go to 0, so it would be a Bernstein type theorem. Right? Okay, so now these are intrinsic balls. This was proven for extrinsic balls by Shane and Simon. So generalization of that. And of course, it's important for this, which is unstated, but it's right up there for everyone to see, that sigma is always an embedded minimal disk. Right? So for the for the catenoid, this would not be true. Right? But sigma is an embedded minimal disk here, so that's why. Now, in general, there's an epsilon regularity estimate that would say that if this was less than an epsilon, then you would get a curvature bound. Right? This is saying if it's less than any constant, you get a curvature bound, as long as it's an embedded minimal disk. Okay, so now let's wrap these things up. So now we're prepared to sketch the proof of A. We have all the ingredients. Okay, so the first thing is, I'm going to fix a big constant, much larger than 1. And now I claim that I can arrange that I can find an S large S, so that the integral over the intrinsic ball of radius beta times S of mod A squared is less than or equal to a constant times beta, say to the 10th, times the area of the intrinsic ball of radius S divided by S squared. Okay, so these are both scale invariant quantities, area divided by R squared, and total curvature. And here this is just sort of a doubling inequality. It says that when I go to a larger scale, beta is much bigger than 1, then this just grows in a polynomial way. Okay, so this follows from A3. Right? In fact, what you would think, you wouldn't think that you'd want beta to the 10th there. You think you'd want beta to the 5th. Right? So as long as I made it anything bigger than 5, it would be easy to achieve this. Okay, so this is the first observation, that we can find such things. So this involves just a little argument. Okay, so the second thing is, so this is saying that we have some control as we go out. The second thing I want to say is that in fact the area must, even this is giving a bound on how fast it grows, I can also get a lower bound on how fast it grows. Okay, so now where does this come from? This comes from this curvature estimate. If this curvature wasn't growing, remember curvature and area are roughly equivalent, if this curvature was not growing, then this would say that the curvature at the origin was bounded by a constant over R squared. When R got big, this would be less than 1. Right? But we said the curvature at the origin is at least 1. Okay, so this is why the area, well, we have some control on what's going on. It also must be growing. Okay, so the second thing is, I can choose large constants. We can assume that the length of the boundary of the ball of radius S divided by S is, let's say, equal to 2 times m times n, with either large. Right. Basically, I can assume that the area divided by S squared, the total curvature, or equivalent to the length divided by S, any of these equivalent quantities is large. Equivalent scale invariant quantities is large. Okay, so that's the second thing. And so this follows, of course, from A4. And the fact that mod A squared at the origin is equal to 1. Okay, so now, what I'd like to do is divide, I look at the intrinsic ball of radius S, here, here's the origin, and now I'd like to divide the boundary of it up into pieces, which I'll call gamma I. So here's gamma 1, gamma 2, so I partition it like this, so that the length of gamma I is equal to m. So this means I get gamma 1 up to gamma to the 2n of these. Okay, so I get each of these pieces. And now I'd like to, these are going to be the directions that I'm going to look in. Okay, so here's some gamma I. Now I want to take this region, and I'm going to, this is a sector, I'm going to call this SI. And this is going to be what happens when I exponentiate over gamma I. Okay, so I look at all geodesics leaving the origin, which pass through this part of the boundary of the ball of radius S. And as I follow those out, I call this a sector SI. This is the region where I'm going to get quadratic curvature decay. So, right. So now, if I add up the curvature for all of the SIs, of course I'm just going to get this. Right? And this, of course, is the area of S divided by S squared. This is, of course, less than or equal to the length of the boundary divided by S. So here I would get something like 4mn, this constant, let's just say a constant mn times beta to 10. Okay, so if I add up all of these total curvatures, this is the amount I get. Therefore, at most half of them, or sorry, at least half of them have to have less than twice the average. Okay, so that means I can find n So after reordering them, I can assume that gamma 1 up to gamma n have integral of mod a squared over si. This is I equal 1 up to n. Less than or equal to the total integral of mod a squared. Less than or equal to the integral of mod a squared over the entire all abraded beta times s. Okay, so this is the total integral that I get, and then divided by n. And then let's say less than or equal to twice that. So this is all, and now this is less than or equal to, right, so if I divide this by 2n, this is the average. So then, I guess this is twice the average. Okay, so, and now this is all less than or equal to, now I get a constant over here, beta to the 10th times m. This does not depend on n. Okay, so I get these sectors. I can choose these sectors which have this bound on the total curvature. This bound on the total curvature is now independent of the number of sectors. Okay, so this, now the next thing I want to notice, right, so since I have this bound on the total curvature, this result A4 says as soon as you have a bound on the total curvature, you get a bound pointwise on the curvature, quadratic curvature decay. So because of A4, we get quadratic curvature decay. So we get mod A squared less than or equal to a constant which depends on beta and m, c which depends on beta and m, divided by, say, r squared on S1 up to Sn. But again, this constant does not depend on the number n. Okay, so here, we've managed to find all of these sectors in all of these directions where the curvature is decaying quadratically. But the bound on the curvature does not depend on the number of sectors. Now I can take the number of sectors as large as I want, just by looking further out. Once I get a large number of sectors, two of them must be very close. Again, everything is trapped inside a ball in R3. So if I have a lot of stuff, two of the points have to be close together. Okay, so now I get two of these sectors with bounded curvature which come close together. Follows that one can be written as a graph over the other and is therefore stable. Okay, so now this sector is stable. As we've seen, stability implies more flatness. Okay, so now I get that this sector is in fact extremely flat. So in other words, the curvature, instead of just being bounded quadratically by some constant, it's bounded by a very small constant divided by r squared. This means the normal doesn't change much. Now since it's embedded, the only way that can happen is it goes around like a graph, is as a multi-value graph. Okay, so this is the sketch of the argument for the first part, A. This is why multi-value graphs develop in there. Okay, so now I'd like to talk a little bit about the other two parts. Maybe it'd be, since I'm going to start erasing things with abandon, maybe I should just pause for a very brief question. Is that
Are we supposed to, last estimate down there, A4 implies you get that quadratic curvature decay on A squared.
right?
As beta gets bigger and bigger and bigger, this constant will get bigger and bigger and bigger.
That's right.
So are we supposed to think of beta as being
Beta's huge but fixed. And then I take n even large relative to beta. Right, so the bound for the curvature here is huge, depending on beta and m, but independent of n. Now, by taking n now much larger, I can make them even closer together. So there's going to be, exactly, you're right, it's going to be, the dependence is very important. There's an order in which constants must be chosen. That's right, so I'll choose beta and m quite big. Then I'll take n even bigger. So even though that bound was relatively weak, they're very, very close together. Right, exactly. Then once I have a weak estimate and stability, I get a sharp estimate and flatness. Exactly. Okay, so right, so this is why these multi-value graphs develop. Now notice that it was very important to use this upper bound on the curvature. This upper bound on the curvature only can be achieved on the scale of where the curvature is, on the scale of the maximum of the curvature. Okay, so that's the sort of thing you get using a blow-up argument, where you look at the curvature may not have a maximum, but if you cut it off by multiplying by the distance to the boundary of the ball, then that function vanishes on the boundary, and you can look at a maximum of that, and you do the usual stuff. Okay, so this is only going to work for us on the scale of the maximum of the curvature, which means the extension result is then crucial. Okay, so instead of mentioning the extension result, I'm going to mention, so maybe I'll say in words again, what's the extension result? Well, if you have one of these, then you can extend it all the way to the boundary. Okay, so that's roughly the idea. I guess I'll leave it to Toby to state it more precisely than that, unless I have a few minutes at the end. So, because what I would rather do is talk a little bit about a tool that is used in the proof of the extension result, and this is what we call the estimate between the sheets. The reason I'd like to talk about this is because I can actually draw some pictures, and hopefully I can give you an idea of what is involved in this a little bit more easily. Okay, so the estimates between the sheets. Okay, so now, again, sigma is our embedded minimal disk. It sits in a ball of radius capital R, and its boundary is in the boundary of the ball. This sort of estimate is going to say that if you know sigma contains something that looks like one of these multi-value graphs, then in fact anything that comes between the sheets of this multi-value graph must itself be graphical. Okay, so that's the estimate between the sheets, roughly speaking. There are various versions which are more or less general. This version I outlined there is a relatively less general version, a little bit weaker, but easy to state. So let's suppose sigma contains something that looks like this. Okay, so sigma contains. Suppose that sigma contains these two graphical parts, right? And now what you're supposed to be thinking about over here is something like half of the helicoid like this, where if you look away from the axis, all you see are these different graphs stacked on top of each other. So suppose sigma contains two graphs like this stacked on top of each other. And let's suppose that this sigma also contains something like an axis. In other words, a way in a small set to connect these stacked graphs. Okay, so sort of like a knife through your Pringles or something. Okay, so here's the little curve which connects the sigma 1 and sigma 2, and I'm going to call this a curve gamma, and I'm going to refer to this as the axis. Okay, because it's going to serve the role as the axis over here. Now what the statement is, which I will not state precisely because it takes a long time to write down a useful, precise version of it, it's just that if anything else, if sigma 3 is another component, which is between these, then sigma 3 is also, I should say, these are graphs. Then sigma 3 is also a graph. Okay, so this is what we call the estimate between the sheets. As long as you have these two sheets like this, which connect by this curve over here off to one side, then anything else which wanders in there must also be graphical. Now, if you think about the helicoid is two halves. One of these halves forms a graph like this. The other half is right in between the sheets of the first one, and it's also a graph. Right? So once you had one half of the helicoid, if you knew there was anything else in there, this would say that you've got the other half too. Okay, so now, how could you prove something like this? Why does it have to be graphical in there? Okay, so let's notice one thing. We're going to use a barrier argument in this. Okay, so let's suppose for a minute that you had a way of forcing a stable minimal surface to enter the region between these two sheets. Right? So suppose there was some way you could force a stable minimal surface to get in there. Well, now this stable surface, remember if you have a stable surface, it's a curvature estimate for it, which says the normal does not change very quickly. Which means that if it was ever to become vertical, it would have to stay vertical for a while. That would force it to cut through the roof, or through the floor. Okay, so that means it cannot become vertical. So if there's a stable surface that's pinched in there, it must be graphical. Now look what happens. It wanders along innocently like a graph, and then it's forced to cut through the axis, which connects the top to the bottom. Because it stays graphical as it leaves, it just chops right through it. Okay, so any stable surface that happened to wander in there would have to cut through sigma. Okay, so that's the idea. So what we're going to want to show is that if sigma 3 was not graphical in there, then I could force a stable surface to wander in that make it stay in the complement of sigma, but on the other hand, notice that it would have to cut through this axis and then get a contradiction. That's the outline. Okay, so now how are you going to get a stable surface to wander in there? Okay, so the first thing to notice is when I said that if you had a surface in there and it was stable, then I said it had to be graphical. Well, all I used from stability there was that if it was stable, then you get a curvature estimate. Okay, so in particular, if you had any surface of bounded curvature in there, it would have to be graphical if it was disjoint from the top and bottom. Okay, so that means if sigma 3 is not graphical in there, the curvature is going to have to be large. Now we already know if the curvature is large, a multi-value graph is going to develop. Okay, so now here I'm going to sort of deceive you a little bit and say that's the way to think about it. That's not actually the way to think about it, because that multi-value graph may start on a very small scale. In order to see that one starts off on an appropriate scale, you need a different argument. But at least it's a plausibility point of view. We now imagine if there's a point of large curvature in here, a multi-value graph develops. So let me imagine that I have this multi-value graph in here. I learned my lesson with the yellow, so let's go with orange. Okay, so this multi-value graph develops in here. Here are some of the sheets of the graph. Okay, now when this develops, I'm going to now follow these sheets off like here a little bit. Right? And now let me intersect the whole picture with a plane which is perpendicular to this. Okay, and when it intersects, it's going to intersect out here, I get these curves, these nodal curves, in sigma 3, in between the sheets of sigma 1 and sigma 2. Okay, now, these nodal curves are going to have to go off to the boundary. You can't have a closed nodal curve in a plane because of the maximum principle for a minimal surface. Right? If the boundary lay in the plane, then the maximum principle would say that the surface lay in the plane. But of course here it does not. Okay, so these nodal curves run off to the boundary. What you might worry about is that a couple of these combine. Another convex Hall property argument makes it easy to see that these actually have to stay disjoint as they go off to the boundary. Okay, so the idea is, suppose these two combine. Then I could get a closed circle in sigma 3. Well, since all of sigma is a disk, this bounds a disk. It's easy to see that this disk, just because of you see what the multi-value graph looks like in here, would have to wander around behind the whole picture. But that would contradict the convex Hall property. I could bring a plane in from this side that would hit it first. Okay, right? Because look at these. So here's the multi-value graph. I have points on each side of this. Right? It wanders around on either way behind it. Okay, so so I can pull these off to the boundary. Now let me look at let me draw a picture of sigma as an abstract disk over here. This is sigma. Think of this as the embedding. Okay, so here's sigma, the disk over in the plane. What is this curve? I could choose a couple of these curves. Let's say the top one and the bottom one. Connect these up somehow in the middle. And I look at this over here. A curve like this. Okay. Now, I can just, from this picture, of course, I can choose some way just to connect this up in the boundary of the disk. So there's some way out here to connect these up. In fact, it probably winds around the picture many times. But there's a way to connect up these endpoints. So this divides sigma into two disks. I can now use sigma as a barrier. And so the ball of radius r, take away sigma, is a good barrier. In the sense of Mies and Yao. Okay? Meaning that I can now take this curve, I can solve for a stable surface in the complement of sigma inside this ball. Okay, so here comes my stable surface. The way the stable surface has been constructed, it cannot just go straight down from here to here because there's a piece of sigma that sits in between. So the only way it can do it is to sort of wander around. It wanders away from its boundary. Now I have a stable surface away from its boundary, but it's pinched, so it's very flat, so it's graphical. It gets shot out the other side. It's a nice graph. It cuts right through gamma, and that's the contradiction. Okay, so that's sort of a rough overview. Okay, so the idea is, if a stable surface wandered in there, was far from its boundary, then I could make it come out and cut through gamma. So the point is, how am I going to force it to go through there? Well, I introduce some fake boundary inside there. But then I have to make sure it leaves the boundary. I use the multi-value graph to do that. Okay, so that's sort of a rough overview of what's involved with the estimate between the sheets. So, so that's the estimate between the sheets. Now the third part of the talk concerns the extension theorem. Okay, so the extension theorem says that once one of these multi-value graphs is born, it extends almost to the boundary. Maybe I'll just close by giving a precise statement of that. Well, I guess my concepts may not line up with Toby, so let me... So this is first paper. So this says, given... Okay, so again, we have a multi-value graph, so you can ask about how many sheets you want, n, well, let's call it m, and the bound for the gradient, let's call that tau. There exists other constants, n, omega, and epsilon, so that if sigma, g contained in sigma intersect, now I'd like actually some restriction on it. I'd like this multi-value graph actually to lie inside a cone, but I'm going to, well, I guess I'll write it x3 squared less than or equal to epsilon squared times x1 squared plus x2 squared. So sigma is contained, this graph is contained in sigma, intersected with this cone, is n value with gradient less than or equal to epsilon over, and now let's say the disk of radius 1, take away the disk of radius r0, and now I need that omega times r0 less than 1, and this is less than capital R over omega. Then sigma g extends to an m-value graph with gradient less than or equal to tau over the disk of radius r divided by omega, take away the disk of radius little r0. Okay, so notice capital R is the outer boundary. This is going out to a fraction all the way to the outer boundary. This now lives on a large scale. Crucial in this dependence is that these constants do not depend on capital R. All I'm going to need is that capital R is bigger than something. The constants themselves do not depend on capital R. That's crucial. Okay, so now combining these two results, you get that as soon as the curvature gets large, a multi-value graph is born. Once it's born, it now extends all the way out to the disk of radius r divided by capital omega. Okay, so this is going to, and now as the curvature goes to infinity, remember r0 goes to 0. So these multi-value graphs then end up converging to graphs in a certain sense, which is, so this, I guess, Toby will explain to you tomorrow how these graphs fit together. Tell you a lot about them embedded them with this. But I guess I should stop there. So thank you very much.
What would you do if notice what
Thank you. I guess what I would do is I would give a little bit of an overview of this. This is a fair bit more complicated than the first part, so I wouldn't really be able to get into it at the same level of detail. but I would be able to explain at least that this extension is done by an iterative process. Okay, so once we have it here, say from R0 to 1, then we go and we extend it from R0 to 2, and then R0 to 4, R0 to 8, etc. And there's a real reason for why you have to iterate it like that. It comes from something to do with this stable stuff, because there's some cutoff on the side, which leads to some issues. When you do this, there's some, because you repeat this iteration of arbitrary number of times, you can't afford to lose anything as you iterate. You can give up nothing in constants. Okay, so that's, essentially. So that's a bit of it, that leads to some serious complications. There's some questions, some things you need to take care of there. One thing, you need to show that it looks like a multi-value graph on each of these scales. Then you have to connect all of these together, right? So just because, suppose you had a surface in R3, and you knew that the curvature was small, the curvature divided by, the curvature was smaller than an epsilon divided by R. This would say that in each region, from say 2 to the n to 2 to the n plus 1, it looked like a graph. But the plane it was graphical over may be changing. How do you show this had like a uniqueness of limit? How do you show that? How do you take care of that? That's a real issue. So we do that in what we call these minimal annuli with and without slips. And that's then there's another question is these sheets as you follow them. Do they come together? Do they pull apart? Maybe you lose sheets. How do you deal with these things? Okay, so a large part of this is dealt with when we study the separation between these sheets. So there's this sublinear growth Toby alluded to before, and then some finer estimates for the separation, which are important to understand. Then there are other questions about the sheets that maybe, I guess that's the best I can say. Thank you very much.